Yes, sir.
So again, the number of students are decreasing, isn't it? Earlier, I
Yes, sir.
used to see almost 100 students. Now it is around 50, 60. Yeah. I have uploaded the PPT of the conduction as well as tutorial 1, tutorial 2, both I have uploaded, but I am not going to upload in future because this is what I see. I generally want everyone to attend at least 50% classes, but it seems like some students don't wanted to attend. They only wanted to get the material from somewhere. But again, I am kind of saying it repeatedly that exams are going to be difficult and proctored. So if you don't attend the classes, don't go through the material carefully, you will have a tough time. But if you attend and go through all the material which I am supplying, then probably you will find it easy. And nothing from the previous exams will be repeated. That is, I am saying it again and again. So if you are thinking that you might be having some previous question papers and that will help you, it's not going to help you. Not at all. All right. So let us start with the today's class. Let me just share my screen. Is it visible to everyone? Hello.
Yes, sir.
So these slides I have already uploaded on Teams. Okay. So I don't want anybody to have in a disadvantageous situation because some of your friends might, get it from some other sources or something. So I want everybody to be at a same page. So no disadvantage to anyone. Okay. So in this, okay, so we started looking at the conduction in the starting. We started looking at the single direction, one directional steady state conduction. Then eventually we added some modification in that. So we started looking at the uh, heat conduction through a variable area. Then we started looking at heat conduction when there is a generation source is there. Then we started looking at heat conduction when the accumulation term is also there, isn't it? And now we are going to look at the heat conduction in multiple directions instead of looking at in one direction, isn't it? So that's what we started looking at in the last class. So this is what we started looking at, isn't it? uh, Multi-dimensional steady state heat conduction. Again, what we said is in this case, we have to look at, since we are looking at multi-directional heat conduction through a flat slab, therefore the equation which will be important to look at is this generalized equation which we have derived for a flat slab. This is the equation which we have derived for a flat slab. 1 by alpha dou t by dou t equals to dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square. Again, this equation is having all the terms there, isn't it? But in the present case, what we are assuming that the heat conduction is taking place only in x and y direction, and therefore this dou square t by dou z square, that term we are neglecting. This get eliminated. Also, there is no generation source present, so psi b by k is also 0, and there is no accumulation. So dou t by dou t, this term also becomes 0. So ultimately what we get is dou square t by dou x square plus dou square t by dou y square equals to 0. So this Laplace equation del square t, this further get modified for a two-dimensional heat conduction, isn't it? Why we are studying such multi-dimensional heat conduction? Because such situation you will see in several practical applications like heat flow in a boiler, isn't it? Or even in many other practical situations where there are multiple metallic parts of different shapes are present, isn't it? So in such cases the heat transfer in multiple direction is what you are going to look at. Typically, this problem is solved numerically. This problem is usually people solve numerically, but just to appreciate the concept, we are solving this problem analytically, and therefore we have considered only a simplified case of two-dimensional heat conduction, and we have not looked at three-dimensional heat conduction. Okay, just to make things simple. So the situation here is like this. We are having a flat slab. In this flat slab, the temperature on the left hand side at x equals to 0 is 0. Similarly, the temperature on the right hand side at x equals to a is also 0. Also, temperature at t at y equals to b is 0, and temperature t at y equals to 0 is f of x. And this f of x we are saying is any function. We don't know a priori whether it's a linear, non-linear, exponential, sinusoidal. We don't know. So this is a generalized function. Okay. What we are assuming that the temperature distribution is taking place only in this plane, but the direction perpendicular to the screen, that is the z direction, along the z direction, the temperature is not at all varying, isn't it? So temperature is not varying along the z direction, and therefore the equation which we need to look at is this: dou square t by dou x square plus dou square t by dou y square equals to 0. This is coming from the generalized equation which we have seen earlier. Okay. Now, in order to solve this particular equation, again we are assuming that we are using in this case the method of variable separation to solve the problem. And in this method of variable separation, what we assume is the solution is having two parts. One part is only dependent on x and another part is only dependent on y. And therefore the solution t is assumed like this. T is given as x, capital X, which is function of x, direction x, and capital Y, which is a function of only y. Okay, so here capital X and capital Y, these are function of only x and y alone. This method is called as variable separation. Okay, now if both x and y has to be independent, isn't it? And these are only function of x. We can put this t in equation number 1, and we can rearrange the terms, and what we can get from equation number 1 and 2 is this: 1 by x d square x by dx square, and that is equals to minus 1 by y d square y by dy square. This specific form we are getting. Now, again, since capital X and capital Y both are function of only x and y alone, that partial derivative which we had earlier, that goes away, and we will have a normal second order derivatives here. Okay, so 1 by capital X d square capital X divided by dx square, and that is equals to minus 1 by y d square capital Y divided by dy square. This is what the equation which we have obtained, equation number 3. Now, since we are saying that x is function of x alone, capital X is a function of small x alone, and capital Y is a function of y alone, and if that has to be true, then this equation 3 should be equals to some constant. It has to be equals to constant, then and then only this functionality is valid, isn't it? So that means 1 by x d square capital X divided by dx square, that should be equals to some constant. Also minus 1 by y, 1 by capital Y into d square capital Y divided by dy square, and that has to be also equals to the same constant. Now, which constant one should select? That is the question. Okay, here, as I said, it will be equals to constant. We can have any constant, but then that constant also should satisfy the boundary conditions. Okay, if we put that constant equals to 0, what we will get is this x is linearly varied, capital X linearly varied with this small x, and similarly this y is linearly varying with small y, and that may not satisfy this boundary condition here. Okay. Also, if we use a positive constant lambda square here, let's say, then we will get the exponential terms. Then you will get the exponential terms or hyper um, sine hyperbolic or cos hyperbolic type of terms you are going to get, isn't it? And that also will not satisfy this boundary condition, because here t equals to f of x we are saying, which is any general function. Remember, any general function can be satisfied only if you are getting the sine and cosine functions. And that you can get only by having a minus lambda square term here as a constant. Of course, this depends on where this negative sign I have put. For instance, if I rearrange this equation and I put this negative sign here, minus 1 by capital X into d square capital X divided by dx square, in that case, I need to use that positive constant instead of a negative constant, so that I will get sine and cosine functions. Is it clear? This is what we have discussed in the last class. All right.
Yes, sir.
This is what is written here. This entire thing is what written here. In equation number 3, both the terms are independent. That means we have to equal it to a constant. Again, in order to get the proper solution of 3, it is essential to select the proper value of this constant. If the value of this constant is selected as 0, equation 3 will give a linear relationship between x and y with respect to small x and small y, and that may not satisfy certain boundary conditions. Also, if we use a positive constant in this specific form, I am saying in this specific form. For instance, if you take this minus sign on this side, then the equation is different. That's what I'm saying. Then in that case, you will have to use a positive constant instead of negative constant. Okay. So if we use a positive constant, the solution of 3 will not satisfy, because if you are using a positive constant, 1 by x d square x divided by dx square and plus minus lambda square you will have. In that case, you will get sine and cosine term, but you will get hyperbolic sine and hyperbolic cosine, isn't it? So that means hyperbolic sine and hyperbolic cosine leads to a exponential terms. So that is not going to satisfy. To put it simply, if the temperature function is given along, okay, here a negative value of the constant, say minus lambda square, will satisfy all the prescribed values of the boundary condition, because it will give the Fourier series expansion of f of x in terms of sine and cosine. Okay. So only in this specific form, if we use minus lambda square, again, why lambda square? Because that simplifies the equation. This is just a constant, isn't it? You take a square of the constant, doesn't matter, isn't it? Okay. So only a negative lambda square satisfies the condition. That is because the function t of f of x is on this x boundary. Okay, but if this function t of f of y would have been there on the y boundary, in that case we would have used a positive constant in this specific form. Is it clear to everyone?
Could you repeat this part again?
Okay. Remember, in this case, t of f of x is only on the x-axis here, isn't it? Correct?
Yes, sir.
But let's say this t of on this t equals to 0, let's say on this x-axis, and instead of this t equals to 0 on y-axis, let's say I put t equals to f of y, any function of direction y.
Sir.
Okay, in that case, I need to use a positive constant.
Right.
Okay. Okay. So let us try to solve this equation now. So we have assumed that the only valid solution we will get if we use minus lambda square as a constant value here. So if I put minus lambda square here, what we get is d square x by dx square plus lambda square x equals to 0. This will be one equation, and the second equation will be d square y by dy square minus lambda square y equals to 0. These are the two equations. Is it clear to everyone, these two equations?
Yes, sir.
Now we can get the analytical solution of both these equations, isn't it? So let's look at the analytical solution of both these equations. So the solution of x will be given by this first equation will be given by a sine lambda x. Remember why we lambda square we have used, because then we have got here lambda x. If you would have used only lambda x, as a constant earlier, then we would have got under root lambda x, and that becomes slightly more complicated. Just to eliminate that, we have used lambda square. Is it clear to everyone? Hello, is it clear?
Yes, sir.
Okay, so x equals to a sine lambda x plus b cos lambda x. That will be the solution of this first equation. Similarly, the solution of the second equation is y is given as c sine hyperbolic lambda y. This is the exponential term. Remember, hyperbolic sine and cosine function can be represented in terms of e raised to power lambda y or minus lambda y, isn't it? Do you all agree? Yes or no? So these are the exponential terms. Is it clear to everyone?
Yes, sir.
So y, capital Y is given as c sine hyperbolic lambda y plus d cos hyperbolic lambda y. So these are the x and y. Remember what the temperature is? Temperature is nothing but the xx into yy from equation 2, isn't it? So both these solution we can multiply and that will give me a T, temperature. That is what we are interested in finding out, correct? Yes or no?
Yes, sir.
So my temperature T is given as multiplication of both these individual solutions. Now let's apply the boundary conditions. Okay, so what is the first boundary condition? My first boundary condition is at x equals to 0. Here at x equals to 0, T is 0, isn't it? So at x equals to 0, T is 0. So again, this c sine lambda y plus d cos lambda y, this can be any value depending on what y I am using. So this cannot be equated to 0. So if this t is 0, 0 divided by this finite term is also 0. So what we get is 0 equals to a sine lambda x plus b cos lambda x, where x equals to 0, isn't it? So a sine lambda x, sine, here x is 0, so sine of 0 is 0, isn't it? So what we get is b cos lambda x. So cos of 0 is just 1. So we get b equals to 0. Do you all agree? This part is clear to everyone, how we are getting?
Yes, sir.
See, we divide this second factor directly to t, isn't it? And t is 0. So 0 divided by this entire factor also becomes 0. Then what we are remaining with? We are remaining with 0 equals to a sine lambda x plus b cos lambda x. Now here x is also 0. So sine of 0 is just 0. So this first factor also becomes 0. Second factor b cos lambda x. So lambda x is again 0 here because x is 0. So cos of 0 is 1. So b equals to 0. Make sense to everyone?
Yes, sir.
Sir, I have a doubt. Sir, like this d square x upon d square x upon dx square plus lambda square x is equal to 0. This is a differential equation. Means we have to solve this differential equation.
Yes.
So, sir,
Yes.
means what is like it comes out to be a sine hyperbolic x plus b cos hyperbolic x.
No, why
So
we are not
how
getting
it comes,
hyperbolic
like,
function here? That's what you are saying?
yes, sir. Means how this solution comes
So
x is
see,
equal
here
to a sine
positive sign
hyperbolic
is
x.
there. Remember, here it is d square x divided by dx square plus lambda square x. Is here plus sign is there. Here negative sign is there. Because of that, you get in the first solution you get a sine lambda x, where in the second you get c sine hyperbolic lambda y. This negative because of this negative sign here. Is it clear? Is
Okay,
that the
sir.
question? So both
Yes,
the
means
equation differs because of the sign here. Here we are having a positive sign, here it is a negative sign. And because of that, one term you get in a normal sine and cosine functions, whereas the second equation you get in terms of hyperbolic sine and hyperbolic cosine. All right.
okay, sir. Okay, sir.
Okay. So this how we have got this b equals to 0 is clear to everyone.
Yes, sir.
Now,
Sir,
okay.
I
Now
have a
let's
doubt.
apply the second. All right. Is there any question?
Yes, sir.
Please go ahead.
Sir, I didn't understand that you first said that we don't need anything in terms of exponentials, but here A equals to
So
0
this
and B
gets no
equals to
no
0,
see
this
see
implies.
see no I didn't say that. I said that if we have see here in this case what we are interested looking at, we will get a function temperature as a function of sine and cosine functions, isn't it? What I said is, I'll repeat again. Here, if I get the temperature here at this boundary in terms of sine and cos, then and then only this boundary condition is going to satisfy. At this location means it will be a function of y because it's varying along this direction, isn't it? Correct. All right. But if I get let's say uh, the functions here in terms of hyperbolic sine and hyperbolic cosine, then hyperbolic sine and hyperbolic cosine can be represented in terms of exponential function, and that will not represent all type of functions. So that's why I don't want it to get the temperature as a function of hyperbolic sine and hyperbolic cosine here, isn't it? That's why we have selected a specific form. Regarding this equation, we have obtained this equation, but you will see that these terms are going to get cancelled out later on.
Okay, sir.
Is it clear to you?
Yes, sir. Yes, sir.
Okay. Okay. So let's apply the second boundary condition. Now second boundary condition says that x equals to a, again temperature T is 0. So in this case now this first term is gone, isn't it? This first term is gone because b is 0. So what we are left with is a sine lambda x into this second factor c sine hyperbolic lambda y plus d cos hyperbolic lambda y, isn't it? Let's apply now second boundary condition at x equals to a, t equals to 0, isn't it? So again, when t equals to 0, this entire thing I can again, divide, isn't it? Because this can vary for any, this can have any value, isn't it? Depending on what value of y I'm using, correct? So again, 0 is here. If I divide this entire thing, that becomes 0. So what we get is a sine lambda a sine lambda a should be equals to 0, isn't it? So sine lambda a again equals to 0, correct? Do you all agree? But sine lambda a is 0 for different values. It's not only at, so it depends on what value of a I am having. Is it lambda I am having, isn't it? So if lambda a is equals to pi, 2 pi, 3 pi, and this 0, see, this 0 term lambda a equals to 0 term, that we have already accounted in calculating this first boundary condition. So that's why lambda a equals to 0. This particular part we are not using here, and only pi, 2 pi, 3 pi we are using. Is it clear to everyone?
Yes, sir.
Isn't it? So lambda a equals to pi, 2 pi, 3 pi. In all these cases, this sine lambda a is will be equals to 0, isn't it? So therefore lambda a, if we rearrange, lambda will be given as n pi by a. Do you all agree? So lambda value will be n pi by a from this.
Yes, sir.
Okay. Now let's put this lambda equals to n pi by a in this equation, in this original equation. Remember b we have already obtained as 0, isn't it? So this we have already omitted. Here this x is remain as it is, lambda is n pi by a. So what we get is a sine n pi x by a, and this second term is also going to become c sine hyperbolic n pi by a into y plus d cos hyperbolic n pi y by a, isn't it? Do you all agree with this equation? And I have put this t equals to tn because we are calculating at individual n, isn't it? So these are, remember here all these values are the eigenvalues. So we will, depending on what eigenvalue I am going to use, I will have a different solution t, isn't it? Correct. So that any nth solution is represented like this. Is it clear? Is it clear? Yes or no?
Sir, n solution means any
Here
means
lambda
any
is going to
any
vary depending on what value of n you are using, isn't it? You are using n pi by a, isn't it? And n is varying as 1, 2, 3.
Yes, sir.
So there are n solutions possible in this equation, isn't it? And each of these solutions are represented as Tn.
Yes, sir. So means there are Tn temperatures in the temperature profile.
No, this Tn is just a value based on this. Actual temperature will be summation of this over 1 to n.
Okay.
Actual temperature will be summation over all Tn. Is it clear?
Okay. Okay.
Does it make sense to everyone? Hello?
Yes, sir.
So,
Now let's put third boundary condition. Third boundary condition is again at y equals to b, t equals to 0. Okay, so put t equals to 0 here. At y equals to b. So y equals to b, if we put it, okay, at t equals to 0 here. So what we are going to get is sine n pi x by a, and this a we have taken inside. So AC we have represented as E, and similarly AD is represented as F. So and again this n pi x equals to n pi x by a is not equals to 0. That is what we have obtained here earlier, isn't it? It's not equals to 0 from the previous analysis, isn't it? Correct. So this n pi x by a is not equals to 0. That means only this bracket will be equals to 0, isn't it? At y equals to b, isn't it? Since this right hand side has to be 0, and since this first factor is not 0, so that means the second factor should be 0. Does it make sense? And this can be 0 only if these two terms cancel each other. Yes or no?
Yes, sir.
Sir, please explain once again why the first factor can't be 0.
So this depending on x can be any value, isn't it? X can be any value. It is not a fixed value like this here. Y is fixed to b, but x can vary to any value. So sine n pi x by a is a finite value, isn't it? It's not non-zero, correct? That is what we have used here, isn't it? The second factor will be finite because y is varying. Yes or no?
Yes, sir.
So here n pi x by a that can vary depending on what value of x I am looking at, and x is varying. X is not fixed. Here only y is fixed in this boundary condition. So that means sine n pi x by a is non-zero, isn't it? That means only the second factor has to be 0. Only the second factor has to be 0, and that means these two terms should cancel out each other. So if both these terms can cancel out each other, I can represent this AC is just E. So I can rearrange this equation. So E will be given by F cos hyperbolic, this is F cos hyperbolic minus F cos hyperbolic n pi B by A divided by sine hyperbolic n pi B by A. Do you all agree?
Yes, sir.
Isn't it? This is what we have got E. This we can put it in this equation again. We can put it in the original equation here, isn't it? We can put it in the original equation. So remember AC is just E. So this E I can replace by this entire thing. Sorry. So by putting everything in the equation, what we get is Tn is given as F sine n pi x by A, and that F I have taken common here, isn't it? F I have taken common, because I will have this E also will have F, and also, sorry, also this AD is also F. So both these F's, remember here also I am having F. Here if I put this E equals to this F, I am having this F term here. So AC will also have a F term, and AD is already F. So that F also I can take it common, isn't it? So that's what we have done. So F is taken common. So F sine n pi x by A, and inside the bracket we left with is minus cos hyperbolic n pi B by A, sine hyperbolic n pi B by A, sine hyperbolic n pi y by A, plus cos hyperbolic n pi y by A. Now we can take even this sine, okay. We can take the sine hyperbolic n pi B by A outside. if I take this sine n pi sine hyperbolic n pi b by a outside here, so what we will get here is f sine n pi x by a divided by sine hyperbolic n pi b by a, and what will be remaining in this bracket will be minus cos hyperbolic n pi b by a sine hyperbolic n pi y by a, and since this factor I have taken outside this bracket, I have to multiply here in the second term, that becomes sine hyperbolic n pi b by a, isn't it? Is it clear to everyone this particular term? Hello?
Yes. Yes.
Now this bracket term can be simplified. This is actually sine hyperbolic n pi a in the bracket b minus y, isn't it? So this entire bracket term gets simplified like this. And outside the bracket, what we will have here is f sine n pi x by a divided by sine hyperbolic n pi b by a. As I said, now in this case, sine hyperbolic n pi b by a, this is a constant term, isn't it? Because b is a fixed value, isn't it? So f divided by sine hyperbolic n pi b by a is a constant term, and that constant term is represented here by a different variable kn. So this tn is given as kn sine n pi x by a sine hyperbolic n pi a in the bracket b minus y, isn't it? Do you all agree? The simplification here.
Yes, sir.
Now again, as I said, this Tn is with respect to an individual value of the this eigenvalues, isn't it? Correct. So whether I am using n equals to pi, 2 pi, 3 pi, etc. Depending on that, I will get different Tn. But actual T will be what? Summation of all these, isn't it? All these Tn. Correct. So that's what we have obtained. The solution of the differential equation may be written as the sum of the solution as like this, where T is varying between T is given as summation of kn sine n pi x by a, summation of this entire term over 1 to infinity, where n is varying between 1 to infinity. Do you all agree? Hello?
Yes, sir.
Yes, sir.
Now in this particular equation, everything is known except that this kn is unknown. This kn is unknown, isn't it? Because this kn we have put as f divided by sine hyperbolic n pi b by a. Even though sine hyperbolic n pi b by a, this can be calculated for a given value of n, isn't it? But f is still unknown here. So kn cannot be calculated directly, isn't it? Do you all agree?
Yes.
Please go ahead. Hello, is there any question?
No, sir, I'm just saying yes.
Okay, all right. So now apply the
Sir, how f is unknown? F is AD. No, AC.
f is a integration constant. If you look at, see what is f? AD, where a is a integration constant and d is also a integration constant. That's what we have used here, a and d. So these are unknown.
Okay.
Okay, so here now this is what the generalized equation which we have obtained. Now apply the last boundary condition. What was the last boundary condition? Y equals to 0. At y equals to 0, t is any function f of x. So if I put it in this equation, what I'm going to get is f of x is equals to summation of 1 to infinity kn sine n pi x by a sine hyperbolic n pi b by a. This is what I'm going to get. Yes or no? This y is 0, isn't it? And this t will be just any function f of x. Do you all agree? Just I have replaced this t by f of x and put y equals to b in this equation, because that is what my last boundary condition is. Correct? Yes or no?
Yes, sir.
Now this equation, if you look at this equation is what? If you, I don't know whether you have studied Fourier series. Have you? Somewhere? Have you studied Fourier series?
No, sir.
Okay, so then look at any standard mathematics book. This is what the equation of the Fourier series. Okay. This is what the equation of the Fourier series, where you can find out this constant kn by rearranging the terms. So the solution of this equation can be directly obtained as like this. So here in this particular equation, remember kn into sine hyperbolic n pi b by a, this is a constant term because here n pi b is known and n is any n which you wanted to look at here, isn't it? And all other are known values. So sine hyperbolic n pi b by a is a constant term, and similarly kn is also a constant term. So this constant term sine hyperbolic n pi b by a into kn, this is a constant term multiplied to a sine n pi x by a, and this is summation over 1 to infinity. This is a standard Fourier series, and the solution of the standard Fourier series is given by this. So this constant term can be obtained here as 2 by alpha and integral 0 to a f of x sine n pi x by a dx. So this is the solution of this Fourier series. This you have to find out in any of these mathematical books. Okay, I will not go in a detail of this. Okay, is it clear? So if you get a summation like this in a Fourier series form, the constant you can obtain directly by rearranging this equation. That's what it is. Is it clear to everyone?
Yes, sir.
So this constant term I have calculated directly from this function because this function is a Fourier series. So this constant is obtained as sine hyperbolic n pi b by a into kn. This entire constant term is given as 2 by a integral 0 to a f of x sine n pi x by a dx. So your take home exercise is to look at this transition. Just look at any of the mathematics book, be it a Erwin Kreyszig or any other mathematics book, you will find this. Okay, is it clear? Just look at Fourier series. Is it clear to everyone? Hello?
Okay, sir.
Yes.
So just look at from this equation, we can directly obtain this constant term kn sine hyperbolic n pi b by a, and that's what I have written directly here. Okay. All right. So once we know this constant term, then you can back substitute in this original equation because this constant term now you have calculated, isn't it? Earlier it was unknown. This kn was unknown because it was in terms of f, isn't it? And f was integral constant, that was not known. But with this substitution, now everything is known because this constant term you are calculating based on the known values now, isn't it? Here a is known and you can integrate this function. You can integrate this function with respect to dx with the limit 0 and a, isn't it? So you can find out this entire constant term. So now this entire constant term is known now. So we back substitute in this original equation. What we get is t of x y, that is obtained as this 2 by a is taken as it is common here, 2 by a summation 1 to infinity. This constant term this constant term kn will be given by this entire integral by sine hyperbolic n pi b by a. So that is what we have done. 1 by sine hyperbolic n pi b by a is into this integral, that is nothing but kn. This entire bracket is nothing but kn into sine n pi x by a and sine hyperbolic n pi a into the bracket b minus y. So this is what the solution of the equation, and this is going to satisfy all the boundary conditions. That's what, because this boundary condition we have put it. Remember here. Remember this boundary condition we have put it, isn't it? F of x, this boundary condition we have put it, isn't it? And that we have obtained in terms of sine functions. All right. Is it clear?
Sir, I have a question. Like this fx is equal to summation 1 to infinity kn sine n pi x by a sine hyperbolic n pi b by a. Sir, why instead of summation we are writing integration 1 to infinity?
Why? Please go ahead. What you are saying? Why we are not writing integral?
Sir, why we are not replacing summation by like fx is equal to summation 1 to infinity kn sine n pi x by a sine hyperbolic n pi b by a.
All right. So see here, what we are saying is, remember these values which we have calculated earlier. These are calculated for this y equals to n pi by a, and these are discrete values. These n are the discrete values 1, 2, 3. You get it? That's why
They
we
are
are
not
using a
continuous.
summation. These are not continuous. Yes. All right. So now here what we have obtained is T of xy, which is nothing but the temperature now. Isn't it? This temperature is as a function of x and y both. Isn't it? So if we calculate all the values with respect to x and y, you are going to get the temperature lines like this. These are the temperature lines which are so okay. So these are the temperature lines. These are the temperature lines which are shown here. Okay, isotherms, because here the temperatures are varying. The constant temperature is varying along these lines, whereas the other lines which are shown here, these are the energy lines. Okay. All right.
Sir, what is the physical relevance of temperature distribution depending upon n? Matlab, what does that n mean?
So see here, small n you are saying.
Yes, sir.
So small n here will be varying between 1 to infinity, isn't it? And the summation of all the Tn will give the actual temperature here, because this here in this case lambda is only valid at these discrete points.
Yes, sir. That is okay. But like, what is the difference between T1 and T2? Matlab, if we have a slab, then there will exist T1, T2. Kya hai
Okay,
ye?
you are trying to look at the physical relevance here.
Yes, sir.
T1,
Yes.
T2, T3. Okay, so see in this case, these are T1, T2, T3. These are the specific solution for individual eigenvalues. These are not the complete solution. These are not the complete solution. Okay, complete solution will be summation of this. Because remember here in this case, this lambda can be different values depending on what n I'm using. So that summation over all these n will be the correct T. And only this Tn, so individual T1, T2, T3 will be the specific solution with respect to lambda. Individual value of lambda, not all. Physical relevance, if you ask, try to, I'm not sure about the physical relevance here, because ultimately we are looking at the temperature, and the temperature is summation of all these, but not the individual term, isn't it? Can we look at in terms of the individual? Is there any physical relevance? I'm not sure right now,
Sir,
but
we
let
can
me
say
just look
that,
at it.
sir, we can say that it represents each and individual temperature in the profile, the
No.
position of each and.
No, I don't think so. I don't think so. I don't think so.
Okay, sir. Maybe the individual terms don't mean anything for
Because
now.
I have shown,
The summation.
only few lines, but you will have infinite lines here,
Hmm.
isn't it? So let me check whether that makes sense or not. Okay. But I don't want it to say yes, as Achintya said. Achintya said, you said these individual lines will be corresponding to each n. That's what you are saying?
No, no, sir. If we put n, then we get every temperature, each value of temperature for every value of n. So it can represent the temperature in the individual temperatures in the profile.
That's
In
what
the
I'm saying.
line.
That's what I'm saying. That's what I'm saying. I am not sure about that. Let me just check it a little bit in more detail. Okay. But right now, not sure. Not sure to me. Okay. But we will come back to this point in the next class. Yes. Okay. All right.
Okay, sir.
Is it clear? Okay. All right. Okay. So this is what the final solution which we have obtained. The final solution is this. Now this final solution is with respect to one boundary condition. Remember, in all three phases we have taken t equals to 0, and only f of x is varying as any general function only at one boundary. Correct? Isn't it? We have solved only one case like this, isn't it? We have solved only one case with this varying, isn't it? This is what the case we have solved. But what I'm trying to say is, very often in a practical application, you have all sort of functions present at all boundaries. It's not that only here the function will be present. It can be here, everywhere, isn't it? Do you all agree?
Yes, sir.
Hello.
Yes, sir.
Isn't it? We have solved only a simplified case. We have solved only a simplified case where we are assuming that the temperature at this boundary is any general function. But at all other boundaries, we have used temperature equals to 0. Correct? But in a normal real life applications, what you will see that here also some t will be f of y, here will be t will be f of y, t will be here f of x, maybe different function. Let's say here I will have t will be f1x, here will be t will be equals to f2x, here t will be equals to f1y, and here you will have t equals to f2y, isn't it? So different functions you can have at all these boundary conditions. I have used only one function now. So can we obtain a temperature profile in such cases? So this entire methodology can be applied to generate the temperature profile in all such cases by doing this. Whenever you have a generalized case like this, you solve individual cases with assuming all other boundaries having temperature equals to 0 and only one boundary is having the functionality. You solve all these 4 cases individually and then you add. Remember this solution which we have obtained in terms of sine and cosine function, isn't it? So these solutions you can use the principle of superposition and you can add it, isn't it? These are additive. Okay, so you can obtain the solution of individual problem by assuming only a temperature functionality at one of these boundaries, isn't it? And then you add all to get the actual temperature profile. Whenever you are having multiple boundaries having the temperature functionality. Do you all agree? Hello?
Yes, sir.
Okay, all right. So this is what, so you can see that even a when we have extended from one dimensional to two dimensional, even the analytical solution became too much complex, isn't it? Right. So, and that is for a very simple case we have looked at. Very simple case of a flat geometry, but assume that if you are having a cylindrical geometry or some other complicated shape, will it be easy to solve analytically? It is not going to be analytically easy to solve, isn't it? Do you all agree?
Yes.
So, okay, so what we are trying to say here is, this entire analysis which we have done just to appreciate the concept. But in a real practical application, most of the time people solve these equations numerically, not analytically, because you might not have a very easier geometry like flat slab. You might be having a very complex geometry like cylindrical surface, and that too a tapering cylinder or something. It's not easy to solve. Get the point? Does it make sense to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, again I come back to another interesting situation. Okay, just a minute. Okay, so this is what we have. Oh, all right, maybe I'll just go back. This is what we have solved. By this equation dou square t by dou x square plus dou square t by dou y square equals to 0. That is what we have solved. Correct? Do you all agree?
Yes, sir.
But let's say I am having a one directional heat transfer only in x direction, but my accumulation term is not 0. Okay, my accumulation term is not 0. That means what? This dou square t by dou y square, this term will go away. This dou square t by dou z square will go away. There's no generation, so this psi v by k also goes away. So what I am left with will be 1 by alpha dou t by dou t, and that is equals to dou square t by dou x square. This is also multi-dimensional, isn't it? Now your another dimension is a time. Do you all agree?
Yes, sir.
So you can do a same analysis to get the solution of such problem also. Does it make sense to everyone?
Yes, sir.
Okay, so same analysis you can extend for this case also, and you can get an analytical solution. In fact, you might find the analytical solution of this in various books. I have not done it.
Excuse me, sir.
Please go ahead.
Sir, but in this case, like in the previous case, we were assuming that for y equal to 0, temperature is having a equal either it is 0 or either it is t equal to a function of x. But if in this case, if we take t equal to 0, then in that case, temperature will have only a single value. It can't be changed, right? Because for a single time, there will be only one value of a temperature.
Okay.
But in that case, for y equal to 0, temperature could be a function also. It could be variable.
Okay, I understood your point. Let me just go back. Okay. So when we have applied all these boundary conditions, remember we have applied this boundary condition. Did you find any difficulty in applying? Maybe I ask a reverse question. So that means it is satisfying here, the boundary condition, isn't it?
Yes.
I just go back. I again go back to the same point. This is what the most critical boundary condition. That is why we are assuming a specific form. Do you all agree?
Yes.
Now let's say in this case, instead of this sine hyperbolic, this constant term I have obtained as a sine hyperbolic here, isn't it? Isn't it? This is a constant term which I have obtained as a sine hyperbolic. Do you all agree?
Yes. Yes.
But instead of this sine hyperbolic as a constant term, I would have had this first term as a constant term, n pi a by something, isn't it? So in that case, I would have had this f of x as a exponential function. Can you see? If I would have used plus lambda square earlier.
Yes. Yes.
So now can you see why we have used that specific choice of lambda square or
No,
sign of?
sir, I was asking that you were saying that in case of if we take time as the another dimension, then also we can solve it in the similar analytical way. But in that case, we won't be able to fix the value because for time, for a single value of time, there will be a single value of t. But here, for y equal to 0, temperature could be a function of x also. So that I was asking.
Okay, so you are saying that this will not be, we will not be able to solve by variable separation. Is it, that is what your question is?
Yes, sir. Yes.
And why you are saying that?
Sir, I was saying that because in case of x and y as the two variables, we were able to change the value of temperature even if we keep the value of one variable fixed. For example, if we take y equal to 0, then in that case t was a function of fx. Means
Here
t
also
can
t
be
is a function of, here also t is a function of x as well as t, both.
no, sir, I meant to say that for y equal to 0, for different values of x, temperature
So
will be
why,
different.
so in that case, boundary conditions will not be like that. Remember, in earlier case, y and x boundary condition we have put because both x and y were variable. In this case, t and x will be the variable.
Yes, sir. So I just wanted to say that if we fix the value of temperature, for example, if we take t to be some constant time, then in that case we can't take t equal to temperature equal to a function of x, because for a given time, for any x, the temperature would be fixed, right? Because
For any
uh, means as we were
no,
keeping
for
the
any x temperature will not be fixed in unsteady state. Why? In unsteady state it will not be fixed.
For a given particular time t.
For a given time it will be.
Means for applying the boundary conditions, we need to fix time and x. Four lines like the previous case, we were taking four boundary conditions in which we were fixing x or we were fixing y. So similarly, in this case, we will have to fix either x or we will have to fix time.
Okay,
so if
I
we fix
just
time,
look. In this case, in that case, we will have this one axis will be a time and another axis will be x.
yes.
Okay, then what is the problem? I don't see any problem there. It will be similar to x and y. except that one equation is a first order partial differential equation. That's it. Other than that, I don't see any difficulty. In fact, such solutions are also there in the book if you see carefully. Okay.
Okay.
Is it clear? So see, in this case, we have used x and y as a variable and we have applied the boundary. Similar way, we can use this y I can replace by t and this will be x. Isn't it? And I can apply the same boundary condition which I have used in this particular problem. The same boundary conditions, isn't it?
Okay, sir. Okay, sir.
Isn't it? This is what we have solved, na? This is what we have solved analytically. Remember?
Yes, sir.
But in this case, we have used this infinite slab. But if I use a finite slab, see, we have already solved it. You can see we have already solved it. But for an infinite slab, but we can solve even for a finite slab. Isn't it? Here, this we have used as an infinite slab, right? But this equation we can even solve for a finite slab with the same analysis what we have done today.
Yes, sir. Got it.
Okay, all right. So this is all about the conduction. This is all about the conduction. We will come back to a very interesting question asked by Achintya, whether all these streamlines, all these isotherms are with respect to individual n. Okay. Okay. Other than that, mostly everything is covered. So let's move to the next topic. Okay. Is it clear or is there any question so far?
Sir, I had a doubt in the lumped heat capacity. Can you go to that slide? Lumped heat capacity concept.
Just a minute. Okay. Please go ahead.
Sir, yes, sir. You said, sir. So you said that in metals there is a tendency that the gradient in the solid body is very negligible as compared to the gradient in the outer surrounding.
Yes.
Therefore, we neglect that and take the whole body for a single as a single temperature.
Yes, yes, absolutely.
Lumped heat capacity. So, sir, it is applicable only in metals because only in metals the thermal conductivity is very high.
No,
But
see,
if suppose
okay.
substance.
It is. I have used that a specific case, but wherever you have the Biot number of this entire body less than, very much less than 0.1, then that assumption is valid. This we have to look at. Biot number should be less than 0.1. In fact, it should be much lower than that. So I may use another. Okay. When a Biot number is much lower than 0.1, then this assumption is valid. Achintya. And when Biot number will be very low? Whenever thermal conductivity is high.
Very high because thermal conductivity is reciprocal of
either
Biot
thermal
number.
conductivity is very high or either the dimension, characteristic dimension of the body is low. Isn't it?
Yes.
Correct. So is it clear? Can we move?
Yes. And one more thing, like if the temperature gradient exists in a body, suppose we are not neglecting it as compared to the surrounding, what is the solution in that case?
So in that case, see, in that case, you will have to solve a temperature profile here. Temperature profile here. Find out the surface temperature here. Okay, we will look at such cases also. So you solve a temperature profile inside the solid, find out the surface temperature here, and that surface temperature will replace this temperature, Tt, instead of the body temperature. Okay.
Okay, sir.
Okay. So that's how we have to solve. But in this case, we are assuming that there is no gradient here. That's why we are taking this entire solid as a single block and finding out the rate of change of energy of this entire block as the energy added by convection directly. Okay. But in other case, you have to solve the conduction equation here, find out what will be the surface temperature here, and then you apply this equation, HA delta T. So here delta T in that case will be T infinity minus T surface. All right.
Yes, sir.
And that T surface can also be a function of time. That can also be function of time, because if you are solving a unsteady state heat conduction here, that means the surface temperature will vary with respect to time. Do you all agree?
Yes, sir. The whole profile will be as a function of time.
Correct, correct. So this equation, a very simplified equation which we are getting, we are not going to get such a simplified equation. In that case, we have to solve a unsteady state heat conduction through this solid first, and then we have to, for applying the boundary condition here, we have to use this convection equation. So this equation will act as a boundary condition.
Yes, sir. Yes.
Okay. All right. So is there any question, or can we move to the next point? Hello? Okay. So let us move to the next topic. This entire slides I have already uploaded in a Teams, so that you all can, go through these in detail. Are my slides visible to everyone? Please ask your friends to attend the classes. That is the only request I am having. Okay, all right. Is it visible? These new slides are visible to everyone?
Yes, sir.
Yes, sir.
Okay, so now we are looking at the concept of heat transfer coefficient. Okay. Concept of heat transfer coefficient we are looking at. Now let me just go through this theory so that we can build on this. Why heat transfer coefficient is required? You will see all the heat transfer books. You will see this concept of heat transfer coefficient, because in a one word, in a one line, if I wanted to give the physical relevance of heat transfer coefficient is by using the heat transfer coefficient, you are simplifying your analysis. Okay, otherwise you will have to, if you don't use this concept of heat transfer coefficient, then you need to solve a complicated Navier-Stokes equation, get a velocity profile, use that velocity profile, then put it in the equation, calculate the variation in viscosity, variation in density, variation in velocity, and all these you have to couple with the thermal conductivity, and then you have to get the heat transfer. Okay, so that is going to become extremely complicated in a it's extremely complicated, because solving even a Navier-Stokes equation is not easy, isn't it? That is why this concept of heat transfer coefficient is used, because all these heat transfer coefficient you can calculate using empirical correlations, so you can get rid of this entire mathematical analysis which otherwise is required if you wanted to solve this problem exactly. Okay, that is a crisp physical relevance of this heat transfer coefficient concept. Okay, so let's look at some of these details. So only few physical situations in which heat transfer occurs in fluid by purely conduction. So this is very important. When we are saying the fluids, there are only few situations in which the heat transfer occurs by conduction. Why? Because in a fluid, there is always the movement of the fluid particles is there, either by a turbulence, or even if there is no turbulence, the increase in the temperature also induce a turbulence in itself, isn't it? So very few situations you will see that the heat transfer occurs in the fluid by conduction. Okay. So clearly the Fourier's law, if you look at the Fourier's law of heat conduction, Fourier's law of heat conduction is applicable whenever the medium is stagnant. Okay, but in a fluid, the medium seldom remains, silent, isn't it? Stagnant, isn't it? It will never remain stagnant. Okay. In practical situation, and therefore heat transfer in such cases primarily governed by convection. Okay. Again, the heat transfer coefficient greatly helps in calculating the rate of heat transfer in convection. Okay, so that I will again give some more detail on this, why it helps in calculating the rate of heat transfer easily in convection. That we will again discuss a little bit in more detail. Typically, conduction occurs due to the vibration of the molecules and the drift of electron, whereas the convection occurs due to the molecular displacement of the fluid. That's what we have seen in the first class itself, isn't it? In conduction, the heat transfer occurs by the vibration of the lattice or movement of the electrons, isn't it? But convection primarily takes place because of the macroscopic movement of the fluid element from one location in the fluid medium to the another location in the fluid medium, isn't it? Do you all agree with me with this? Hello?
Yes, sir.
This we have already seen. Now consider a fluid having a bulk motion. Let's say there is a movement in the fluid medium. If the flow is laminar, the fluid elements or ensembles move in an orderly or a streamline flow. So that's what happens in the laminar flow, isn't it? Fluid moves in an orderly manner, isn't it? Correct. That's what probably you have looked at in the experiment in your fluid mechanics, where you are injecting a dye. So you will see a very good streamlines you can see in a laminar flow. But when we look at the turbulent flow, in a turbulent flow, the fluids move in terms of eddies, in terms of the fluid chunks are mixing with each other in a random manner, isn't it? But the average net displacement you can find out in the direction of the flow. Okay, so in both these cases, laminar as well as in a turbulent flow, whenever the fluid elements are moving from one place to the another, it is taking the heat energy with it, isn't it? And it is transferring the heat from one location to the another location if both the locations are at a two different temperatures. Do you all agree? Isn't it? So that's what is been written here. In either case, a moving fluid element carries with it a heat energy as it moves from one point to another, and thus contribute to the rate of heat transfer in the event of there being a temperature gradient. Okay, so now look at the movement of the fluid across the solid. So when the fluid flows over the solid surface, the velocity of the fluid exactly at the boundary, exactly at the surface is zero because of no slip condition, isn't it? So velocity is zero at the boundary of the solid surface. And as you move away from that boundary, the velocity will start increasing and eventually it reaches to the free stream velocity, isn't it? Correct. That's what is the standard boundary layer concept is, isn't it? Do you all agree? Isn't it? Hello?
Yes.
So eventually you can see that doesn't matter whether a flow is laminar or turbulent. In both the cases, you will see this no slip condition at the surface of the solid, and very near to the solid surface, you will see that there is a stagnant layer. There is a stagnant layer where the velocity is practically zero, isn't it? Almost zero. And this layer, which is very close to the solid surface, this particular layer is responsible for the resistance to the heat transfer. So in fact, this particular layer accounts most of the resistance for the heat transfer because the conduction is governed in this layer, isn't it? Again, as the velocity increases, the thickness of this particular stagnant layer decreases, isn't it? Correct? Do you all agree? Do you all agree or not? So it doesn't matter whether a flow is a laminar or a turbulent, a layer near to the solid surface is always at a velocity very close to zero. And this particular layer is responsible for most of the heat transfer resistance because in this particular layer, the heat transfer takes place by a conduction, isn't it? So there is no bulk motion of the fluid. So in fact, this is the rate limiting, layer. So most of the resistance to heat transfer is caused in this particular layer itself. Okay, but this layer is a fictitious layer. Why I am saying fictitious layer? Because as you increase the velocity, thickness of this layer is going to decrease. Thickness of this layer is going to decrease. And therefore, as you increase the velocity, you will see that heat transfer increases. Heat transfer increases. Do you all agree?
Yes, sir.
Okay. So that is what we have written here. So irrespective of the nature of the flow of the fluid, bulk fluid, a fluid layer near the surface always remains laminar. The thickness of this layer decreases with increase in the velocity of the bulk fluid. This thin layer of the fluid at the surface accounts for the most of the resistance to heat transfer. A higher velocity of the fluid, the resistance becomes smaller. Okay, this is what we have written here. So if the resistance to heat transfer is known, okay. Now let's try to build on the concept of heat transfer coefficient. Okay. If this resistance to heat transfer is known, then we can directly calculate the rate of heat transfer by using this equation, isn't it? We can use this equation and we can calculate the heat transfer directly. Okay, but finding this heat transfer resistance is not easy, isn't it? Although this resistance can be calculated in principle, if the velocity distribution of the fluid is known clearly, but in a practical application, you will see that this exercise becomes difficult in a great majority of practical flow situation, primarily because the velocity distribution is not well understood or the problem is formidable mathematically. So what we are trying to say is, if the heat transfer resistance is known accurately, then you can calculate the rate of heat transfer directly. But calculating this heat transfer resistance is not easy because you need to know velocity distribution for that. And velocity distribution, calculating the velocity distribution is not always easy. For a laminar flow, you can calculate. But let's say if your flow is turbulent, it's not easy. And also in most of the situations, it becomes practically, impossible to solve. Why? Because you need to solve a laminar this Navier-Stokes equation, and solving a Navier-Stokes equation accurately is not easy. Do you all agree? That's why we are saying it's a mathematically formidable, isn't it, to solve? Do you all agree? Do you all agree why? What is the difficulty in this? So in such cases, a pragmatic approach is used to overcome the difficulty. What is pragmatic approach?
Empirical, I think, sir.
Sorry, am I audible now?
Yes, sir.
Hello. Sorry,
Yes,
some internet failure occurred. So is my slides visible?
yes, sir.
Okay. So what we are saying is, in such cases, a pragmatic approach is used, and in that what we are doing is we are assuming this h to be some value. We will calculate this h in a much more easier way than calculating this h by first principle. Okay, so this h can be calculated from empirical correlations. These empirical correlations are based on some data generated over the different geometries for different situations, and based on that this h can be calculated, and then this h can be used in this equation to calculate q, and this is what the Newton's law of cooling is. Okay, so q is given as ha delta t. Okay, so there is no fundamental derivation of Newton's law of cooling. It is based on some practical application. We are calculating all this resistance uh, uh, in terms of this h. Okay, so all these unknown terms which are difficult to evaluate, like velocity distribution, effect of thermal conductivity, effect of density, effect of viscosity, everything is coupled in this particular coefficient called as h, which is nothing but heat transfer coefficient, and that's why we are calling this approach as a pragmatic approach. This is not from the first principle. This is based on the practical application. Okay. Do you all agree? Hello?
Yes, sir.
So what we are saying here is, if you wanted to solve this problem, whenever there is a fluid is moving, in such cases we need to calculate first velocity distribution, and then that velocity distribution has to be accounted in calculating the resistance, and then that resistance should be used for calculating the heat transfer. So it becomes very difficult because calculating even the velocity distribution is not easy in a practical situation. So to ease out, another coefficient called as a heat transfer coefficient is used, which accounts the effect of velocity distribution, change in viscosity, change in density, all sort of uncertainties are included in that. And this heat transfer coefficient is then calculated using the empirical correlations, which are based on the data generated over the years. So that is why we are calling this as a pragmatic approach. Okay. Okay, so here in this particular equation, Q is given as HA delta T. Delta T here is going to be surface temperature minus the bulk temperature. Okay. Here H is the heat transfer coefficient, A is the area of the heat transfer. The heat transfer coefficient, again, we are calling it as a phenomenological constant. Okay. So unlike the thermal conductivity is the property of the material. It's a fundamental property, but H is not a fundamental property. H is dependent on several things. It depends on thermal conductivity, it depends on velocity, it depends on viscosity, it depends on density. Okay, so H is not a fundamental constant. H is a phenomenological coefficient. Okay, do you all agree? Hello?
Yes, sir.
So it is based on the observation that the rate of convective heat transfer is proportional. See, this entire equation is based on this observation. Rate of heat transfer is proportional to the driving force. That's it. It is based on the observation. It's not derived from the first principle. Do you all agree? Yes or no? Hello? So this Newton's law of cooling, this equation is a Newton's law of cooling, where the heat transfer is given is proportional to the delta T, temperature gradient, temperature driving force, sorry, temperature difference. Okay, so this is based on the observation. Okay, so again we can rearrange this as Q is HA delta T. So H will be given as Q by A delta T. So this is nothing but Q by small q by delta T. So it is nothing but how my flux is changing with respect to the change in temperature gradient, temperature difference. That is what is called as heat transfer coefficient. Okay, so heat transfer coefficient combines in it the effect of velocity or motion in the medium and also the properties like thermal conductivity, viscosity, density of the medium, etc. So we will look at this thing again little bit in more detail, where you will appreciate why I am saying it is not only dependent on thermal conductivity but also viscosity, density and velocity. Okay, so that we will look at in the next slide. Again, as so H is higher for forced convection compared to the free convection. Okay, all right. So let's look at heat transfer coefficient as a film coefficient. This will give you some insight why I am saying that the heat transfer coefficient is a function of velocity, density, viscosity, etc. Okay, so if you look at the heat transfer, whenever there is a movement of the fluid is taking place, let's say this is the hot surface and this is not moving and the fluid is moving, let's say, across the hot surface. You can see that the fluid layer very close to the solid surface will be almost stagnant, isn't it? So and this particular film, which is very close to the solid surface, you will see that the velocity is almost zero. So most of the resistance is offered only in this stagnant film. Do you all agree? Do you all agree with me? So if you look at the temperature profile is something like this. So most of the temperature difference occurs only in this flat, only in this small film which is there close to the solid surface, and then there is a bulk motion. So here you can see that the temperature is varying as shown by the red line, but most of the temperature gradient is occurring only in this film, a small film, a stagnant film which is close to the solid surface. Do you all agree? Yes or no?
Yes, sir.
Yes, sir.
So when we are saying that this fluid element is stagnant in this film, the fluid element is stagnant very close to this surface. This is the hot surface, isn't it? This hot surface is not moving. This is the fluid which is moving, isn't it? And this is the film. This is the film. This is the film of the thickness delta. Okay. Now what we are saying that in this film the fluid is not moving. That means this is a stagnant film. So when the fluid is stagnant, we can apply the Fourier's law of heat conduction. Do you all agree? Remember, we said that the Fourier's law of heat conduction is you can apply whenever the fluid element is not moving, isn't it? In a stagnant film, correct? So we can apply Fourier's law of heat conduction here. Yes or no?
Yes.
So now here Q will be given by what? Ka delta T. Delta T will be what? Ts minus bulk temperature T naught divided by thickness of this film, which is delta. So we can get K by delta A Ts minus T naught. Now this K by delta we can represent as H, and it can be given as H delta T. Can you see how we have derived this Newton's law of cooling from?
So this whole film is not moving. Means you said that we can apply Fourier's law of heat conduction when a layer is not moving. So this
Yes.
whole film is not moving.
Yes, this film is stagnant. Remember, I said that doesn't matter whether a flow is a laminar or turbulent, a layer very close to the surface always remains stagnant. Isn't it? A fluid layer which is close to the solid surface will always remain stagnant. Doesn't matter whether it is laminar or a turbulent. Isn't it? A small layer which is very close to the solid surface will be at a zero velocity because of no slip condition. Do you all agree? And that is what film we are assuming here. Isn't it? Yes or no?
Yes, sir.
So this film is almost stagnant. Of course, there will be some movement. It's not absolutely stagnant, but it will not be as high as the movement which is present in the bulk of the fluid. Do you all agree? So we can assume a Fourier's law of heat conduction here in this region with some reservations, isn't it? Do you all agree? Yes or no?
Yes, sir.
So the same thing we have done. We have applied the Fourier's law of heat conduction. So that is given as Q, capital Q is given as minus Ka delta T by delta. So that is K by delta we can represent as H. So this becomes a Newton's law of cooling, H delta T. Do you all agree? Yes or no? Hello? Does it make sense? So the definition of H is also we can obtain thermal conductivity divided by thickness of the film. That gives you the heat transfer coefficient. Now, as I said, this heat transfer coefficient depends on several things. It's not depends. So as I said, heat transfer coefficient depends on thermal conductivity. So that is evident directly from this equation. Also, this heat transfer coefficient depends on viscosity, density, and velocity, because all these factors are going to, impact on this delta. Delta is what? The thickness of this film. And thickness of this film depends on velocity profile, it depends on density, it depends on viscosity. So clearly your heat transfer coefficient includes the effect of not only the thermal conductivity but also viscosity, velocity and density. Do you all agree? Do you all agree?
Yes, sir.
But it's not easy. So you can say that I can calculate H directly using this equation. It's not easy because delta you cannot ascertain accurately. You cannot obtain this value of delta easily because this is a fictitious film. This is a fictitious film, isn't it? You cannot calculate delta easily. And that is why very often this H is calculated using some empirical correlations. Can you see the point? Hello? Does it make sense? Okay, so we stop here. We will continue this discussion again in the next class. So I have uploaded the conduction PPT. I have uploaded tutorial 1 and tutorial 2. Both I have uploaded on Teams. Also the tutorial 3 work that tutorial 3 statement is also uploaded in Teams. You can download and you can start solving. Okay. So thank you everyone for joining. Please ask your friend to join the class. That motivates the instructor. Okay. So if you join in more number, that is going to make me, is going to inspire me to do even better. Okay. All right. So again, okay, sorry. I just thought of, discussing something. So when we are having the minor one,
Sir, it's after 14th, 15th Feb. I guess the proper schedule is not there yet.
From 14 February. 14 February.
Acha, okay. So do you wanted to have a quiz before that, or you wanted to have a quiz after the minor? Remember, we will have, huh?
Before.
So it doesn't matter because all quiz and minor, everything is going to have a same weightage. So it doesn't matter. You can have it before, you can have it later. It's okay. All right. Okay, we will discuss it in the next class. All right. Okay. So let us stop here. Stay safe and see you on Wednesday.
Thank you, sir.
Thank you, sir.
Thank you, everyone.
Thank you, sir.
Thank you, sir.